So, good afternoon, everybody, and thank you all for joining us. So we're pleased to welcome back those who've been with us since the fall, and we're especially pleased to welcome those of you who are new to the SRI seminar series. My name is Dennis Walsh, and I'm a philosopher of biology in the Department of Philosophy and the Institute for the History and Philosophy of Science and Technology and the Department of Ecology and Evolutionary Biology here at the University of Toronto. And I'm also delighted to say a research lead at the Schwartz Reisman Institute for Technology and Society, which is also a part of the University of Toronto. The Schwartz Reisman Institute seminar series is a weekly event that features an academic researcher introducing the work they've done or work they are currently working on and directions they're exploring. And this is an event for academics, students, and the public, anyone who is looking to unwind and interact with others interested in ethics and the role of AI in our lives outside of classes and meetings. So for those of you who are unfamiliar with this, I'll introduce you to the structure. First, we have a wonderful guest speaker who will speak for 45 minutes. And then we'll have a 45-minute discussion break. We encourage you to ask questions in the chat and share thoughts. Our speaker today has said to me that he'd be happy to take clarificatory questions during the course of his talk. So if I see a message in the chat of the form, "What do you mean by X?" I will interrupt him and have that person ask this question. But I guess we'll leave the general discussion until the end. So now it's my pleasure to introduce the first speaker of the new term. This is Richard Watson. Richard is an associate professor in the Agents, Interaction and Complexity Group at the University of Southampton, the School of Electronics and Computer Science. And he's somebody whose work I've known and admired for quite some time. Richard is unique in my experience because he combines formal background in AI, but also theoretical training in evolutionary biology. So he received his BA in artificial intelligence and MSc in knowledge-based systems from Sussex, and then went on to Brandeis and did his PhD in computer science, which resulted in 22 publications and a dissertation addressing the algorithmic concepts underlying the major transitions in evolution. Wow. But then he went on to a postdoc at Harvard University Department of Organismic and Evolutionary Biology, which in my view is the best in the world, which provided training to complement the computer science background. So now he has over 80 journal and conference publications on topics spanning artificial life, robotics, evolutionary computation, population genetics, neural networks, evolutionary theory, and computational biology. He's the author of the book Compositional Evolution, The Impact of Sex, Symbiosis, and Modularity on the Gradualist Framework of Evolution that came out with MIT Press. And his current research program seeks to deepen our understanding of biological evolution by expanding the formal equivalence of learning and evolution, in particular, using connectionist models of cognition and learning. One key paper that I encourage you all to look at if you get the chance is his 2016 Tree article with your Sathmare, How Can Evolution Learn? And also, I'm delighted to welcome Richard, because as I say, this is somebody whose work I really, really admire and value. And Richard, I hope I haven't taken up all your 45 minutes, but if not, I'll pass it over to you. Take it away, please.
That's so kind of you, Dennis, to spend so much time introducing me. I imagined it would be 2 sentences, but that's very kind of you. Let me start sharing my screen, shall I? So firstly, thank you to you for inviting me, and thank you to everybody here for taking the time to come and listen and discuss this with me. I'm very keen to have your discussion and input on what I'm going to talk about, because this is a talk where the middle section of this talk, the sciencey bit, is something that I've been developing over the last few years and is relatively well established. But here, for essentially the first time, I'm presenting it in a context which describes its larger implications for society and for us and how we live as individuals, and how that fits with much bigger worldviews. So I'm very keen to get your feedback on that, and it's all about working together. So let's do that if we can. Thank you. I'll begin. If I can advance the slide, which I cannot. Yes, I can. I'm going to minimize the faces. There we go. So here's the setup. The prevailing scientific view is that self-interest and competition are natural and logical. Natural because evolutionary theory tells us that it's all about survival of the fittest, and logical because, well, the only logical action for me to do is what's best for me. And that way of seeing things is consistent with a worldview, largely Western in origin, now global, that creates isolation between us, greed and unsustainable exploitation of one another and resources that's harmful to us as individuals, as a society, and the global community and other living things in the biosphere. There's a completely different worldview, familiar within Eastern wisdom traditions, that doesn't see the world like that. It sees it as a larger tapestry of living things, a harmonious web of life, if you like. And in this view, there's no aim to win or outcompete others, only to find harmony with nature, to live with ease and balance, playing a role contextualized within the greater whole. And I have been particularly grateful to Jeremy Lent's work here to describe how these worldviews have developed and shaped human history over centuries. In his works, The Patterning Instinct and The Web of Meaning. So that Eastern worldview is more consistent with the idea that cooperation, synergy, and working together with respect for nature and one another is natural and wise. It resonates with the Gaia hypothesis as the biosphere being like an organism, in ecological communities being networks of organized functions that recycle resources, for example. And on a personal and social level, it resonates with the idea that it isn't about competition and it isn't about self-interest, it's about love. Everything is connected. Love is the way. I'll use love as the shorthand for this worldview. Well, that's just great. Too bad, it's baloney. It's a jungle out there. It's dog eat dog. It's all against all. That's nature's way and the way of the world. You might not like it, but that's the way it is. I'm parodying a position, of course. Now, some obvious objections to this rather crude way of seeing the world is that, well, nature is full of cooperation. There's cooperation in social animal behavior from bacteria up to primates. But social evolution theory points out that cheating is always preferable. If an individual can take the benefits of the cooperative group without contributing themselves, they will proliferate more. Well, what about the transitions in individuality? The transition from unicellular life to multicellular organisms, for example, is an example of cooperation par none, that all of those cells working together is an excellent example of cooperation, and it's fundamental to the origin of complex adaptations in life, in living systems. But again, social evolution theory tells us, well, but this is explained by genetic relatedness and the selfishness of the genes and cells involved. But come on, although there have been some notable atrocities, humans are basically peaceful, but only to the extent that we deny our nature to be self-interested. Well, we're not denying our nature, you say. We're wired to be nice. Neuroscience has stuck the electrodes on our heads and demonstrated that our brains are wired to be pro-social. But they were only wired that way because in our evolutionary history, it enabled us to survive and reproduce better than others. But anyway, social well-being is logical because we're all in it together. But cheating is still preferable at the individual level. If you can get away with it, why wouldn't you? Well, you wouldn't because pro-social organizations prosper and survive better than those that are antisocial. But that's just survival of the fittest reasoning again at a different level of organization. Now, those are, I would argue, not just empirical facts, not just a case-by-case sort of reasoning, but there's a fundamental blanket argument beneath all of this. It just can't be logical or natural to cooperate. And all of these phenomena, whatever phenomena you find, have to be explained in terms of self-interest. Unless there are incentives or selection that operates at some other level of organization, but even then it's still competition at that level that's doing the work, that's the prime mover. Why so sure? Why so absolute about this? Well, first there's the logic. it can't be rational for me to choose to do something that's not in my interest. If I choose to be pro-social, it's because that's the best option for me. Or if I just like being nice, then it's still what I prefer with respect to my utility function. And if I can't help being nice because that's the way I'm built, well, then it wasn't a choice at all. I don't see any way out of it. If you accept the concepts of individual and of interest, of benefit and utility and incentive, or any kind of optimization principle, I don't see how you can come to a different conclusion. You might not be very good at optimizing the thing you were supposed to optimize, but that's a different issue. It can't be rational not to optimize it. Now, economics and social behavior and evolutionary biology seek to explain observations or strategies as rational under self-interest by redefining the maximizer or the maximand. An example of redefining the maximizer is to say, well, this bee appears to be altruistic in stinging the prey that was attacking the nest and giving up its own life, but it's not really, because it's the selfish gene that's doing the work. Or this human chose to spend their resources on punishing others instead of walking away with the cost for themselves, but we explain it by optimizing some other utility functions such as reputation or such like. So what about the nature part? Well, natural selection, heritable variation, and reproductive success is all about differential survival and differential reproduction. That's the mechanism that explains all biology. Competition is fundamentally the prime mover in nature. I love Dawkins. I love him because he's so good at putting into eloquent words and describing exactly what it is that other people are thinking. And he makes the case very eloquently that not only is natural selection as a matter of empirical fact the mechanism that explains all biological adaptation here on Earth, but in fact, it's the only possible mechanism that could produce spontaneous adaptation anywhere in the universe, hence universal Darwinism. It's the only way that it can work because anything else would require some sort of mystical mechanism of directed change, and there just isn't one. And Darwin is thereby placed on a pedestal in universal Darwinism. Now, universal Darwinism is not just a claim about life on other planets and how it might be adapted or not. It articulates a certainty about how things can and cannot be adapted here on Earth. Specifically, if we're looking at a system where natural selection doesn't apply, it can't be adapted, which means that nothing above the level of a Darwinian individual can be adapted. Loose social groups, ecological communities, the biosphere as a whole can't be adapted because they're not evolutionary units. There isn't a population of biospheres, differential survival and proliferation of planets is not a mechanism that applies at that scale. So these systems might be complicated, but they're not organized for holistic adaptive function. And this is not just something that I'm saying. If you see debates on group selection or Gaia theory or the extended evolutionary synthesis, where people like Welch say, you just want things to be nice, but they're just not, you're soft in the head. These are arguments, real arguments that people actually write down. So since Darwinism is the exclusive mechanism of adaptation, science and logic says, well, the web of life, whatever that is, can't be harmonious because the web of life isn't an evolutionary unit. It can't have any adaptive functional organization, let alone harmony. It's just an unorganized mess, each part fighting for themselves. Now, does this produce a real conflict, a genuine conflict of any kind between love, if I'm using that as the shorthand for that view that we should welcome working together and symbiosis and mutualism and organizational structures of those kinds, and science and logic on the other hand? Well, one way to say that it doesn't produce any real conflict is to say, well, the science is right, what's the problem? There really isn't any evidence of cooperation that's natural in large systems, that no evidence that they're adapted. This is a non-problem. Another is to say, well, the logic is right, but what's the problem? Greed really is good. And it doesn't require a fictional Gordon Gekko to tell us that. Profit maximization, performance optimization, and free market competition are all advocated by real people as the right thing to do. Another approach is to say, well, sure, the science is right, but science isn't about values. What you do with the science is up to you. And another approach, which I wasn't so familiar with until I married a yoga teacher, is science schmience. Who cares about science? I believe in love. It's a higher and ancient truth. Well, on the other hand, you might think, no, there is a real conflict here. The science is right. It describes how nature works. It describes how things work. And that's a conflict. We need to figure out how to counter that, how to live with it or fix it or alleviate it. We have to change our ways. We have to make choices about how we behave. It's complicated. We have to muddle through. We have to talk to each other and find a way. Perhaps stronger global governance and regulation is needed. Or perhaps globalization is bad and localization is better because it provides tighter feedbacks, perhaps at multiple nested layers, as Eleanor Ostrom would advocate. Her work suggests that it can work despite the science being right, that self-interest is logical. But another way in which there's a real conflict here could be that the science isn't right. As Ostrom's work shows that it can work in practice, that if something can work in practice, it can work in theory. What we need is a theory for how it works. Now, certainly human selfishness has a long history, long before the theory of natural selection, but it's my contention that the scientific claim that selection is the only process possible of producing adaptation reinforces and sustains the contemporary Western worldview, justifying and advocating selfishness, exploitation, and discompassion at personal, societal, and global scales. And my claim is that universal Darwinism is not correct. That evolution by natural selection is not the only mechanism of creating adaptive organization possible in the natural world. Competition, survival of the fittest, is not the only way that systems can improve spontaneously. There's a different mechanism of adaptation, one that does not depend on differential survival and reproduction, where self-interest is not the prime mover. Natural systems that are not evolutionary units can thereby exhibit adaptation in the sense of increasing their ability to resolve conflicting constraints among their components, which you might call an increase in harmony. And that means that the social systems that we co-create and participate in can likewise exhibit systemic intelligence without design or selection. And it works through the differential easing of relationships, and supporting the differential easing of relationships, not competition, not profit maximization, not performance optimization, enhances systemic intelligence. And in fact, competition, profit maximization, and performance optimization degrade the systemic intelligence of the system. It's a localized incremental process that operates without any centralized control or global feedback. So that's the big picture, the worldviews and the role of universal Darwinism in it. So now I better tell you about natural induction, the antidote to universal Darwinism that I'd like to introduce. So natural induction is a process by which a dynamical system becomes adaptively organized spontaneously. It's natural in the sense that it occurs in any dynamical system with suitable properties without being selected or designed for that purpose. And it does not require natural selection, although the way that natural selection and natural induction interact with each other is rather interesting. Natural induction doesn't apply to everything, like natural selection doesn't apply to everything, but it does apply to some systems that natural selection does not. Notably, it can explain how dynamical systems that are not evolutionary units, including ecosystems and societies, can learn, adapt, and solve problems in a quantifiable sense. And it doesn't need very complicated assumptions, and it's supported by well-founded learning theory. So let's go back to the beginning. What's induction? Induction in logic is the production of general rules from specific examples. For example, this colorful thing tastes good, that colorful thing tastes good. By induction, colorful things taste good. Or this one is white, this one is white, this one is white, all swans are white. Now, you'll notice, or you'll know if you're familiar with induction, that inductions do not follow logically from the observations. The conclusions can be wrong, even if the context is correct. Before I tell you more about induction, I have to tell you my favorite joke about induction. There are two kinds of people in the world. One, those who can extrapolate from incomplete data. So even though induction conclusions are not necessarily correct, induction is nonetheless fundamental to learning. If you can't do induction, then you can do well on the examples that you've seen before, but that's just memory or rote learning. Real learning requires you to do well on the examples you've seen before and on other novel cases that you haven't seen before. That's generalization. Well, how do you do that? The way that brains do that might be complicated, but in artificial machine learning, in neural networks, you can do it very simply with associative induction. Associative induction just means learning what goes together. It only requires very simple local rules, such as neurons that fire together wire together, which just means that the more that two things co-occurred in the past, the more they become likely to co-occur in the future. That's a positive feedback on correlations. And that can do all sorts of cool things. It can do associative memory and recall, classification, reinforcement learning, generalization. It can build low-dimensional models of high-dimensional data sets, and it can learn to solve constraint optimization problems better with experience. So, whereas brains are an example of a system that's evolved to do induction, and machine learning as examples of systems that are designed to do induction, natural induction occurs spontaneously in dynamical systems with suitable properties. It's the change in the connective organization of a dynamical system that results indirectly from the pattern of forcing it experiences, resulting in learning and increased optimization ability. How does it work in 4 easy steps? Well, it might not be too surprising to you to know that clever things like machine learning systems or natural systems that can do associative learning can do global adaptation and exhibit global adaptation ability in networks of simple components, like a learning neural network. The mechanism necessary to make that work is simply, or can be, unsupervised distributed associative learning, which doesn't require any centralized control or global feedback. I'll say more about how that works in a moment in all these steps. And unsupervised distributed associative learning is just positive feedback on correlations. The more things have co-occurred in the past, the more they change their connections to co-occur more in the future. And the last part is that viscoelastic connections do positive feedback on correlations naturally. What's a viscoelastic connection? It just means a connection that isn't perfectly elastic, a connection that gives way slightly under stress. So when you push a spring to get together, it pushes back, and when you pull a spring, it pulls in. But if you pull it too much or you keep it extended for long, its natural length creeps to make it resist the forces that it's experiencing less. Or if you compress it for a long time or too much, it gives way under that stress and the natural length of the spring decreases. All springs do this because no springs are perfect, except in idealized mathematical cases. And viscoelasticity, well, that's like what most elasticity is, because most elastic interactions between things are not perfect. And the way that they changes in a way that makes whatever the current states are, the particles on the end of the springs, whatever they're doing, becomes more likely to occur again. So if you increase the natural length of the spring, it makes it easier for the two particles to be far apart. If you decrease the length of the spring, it makes it easier for the two particles to be closer together. That's the positive feedback on correlations that's necessary. And it's natural because you don't need to design a spring to do that. It's just energy minimization. When the string is under stress, energy minimization in the molecular material of the spring causes it to relax. And as it relaxes, it creeps, and it creeps in the direction that makes the current states more likely to occur again in future, not less likely. So when we put that all together, it means that networks of viscoelastic connections, whether they're built out of particles connected by springs, or people connected by social relationships, or species in an ecosystem connected by competition coefficients, are capable of producing the same kind of global adaptation ability that a learning neural network can, and do so naturally without selection or design. This applies to any dynamical system described by a network of viscoelastic connections experiencing episodic stress or perturbation. Viscoelastic, as I said, means that the connections give way a little under stress. And the differential stress, not all of the springs in the system, not all of the connections of the system experience the same stress, is determined by the experience or history of the system. And they change in such a way that eases the frustrations over multiple episodes. Let's return to that episodic stress remark earlier. If the system has viscoelastic connections, but it isn't experiencing an episodic stress, it's just experiencing one stress, then the springs will give way in such a way that reinforces that one experience. That's like overfitting in a learning system. And if you do that, that's the only thing it'll ever do. But if instead the system is applied, a stress is applied to the system and then you back off, and then a stress is applied to the system and then you back off, or if you're letting the system relax from a high energy state to a low energy state, and then you heat it up and you cool it down again, and you heat it up and you cool it down again, then in that case, the system visits a distribution of attractors over its experience. And that results in an associative memory of that past experience, associative because it's stored in connections rather than in unitary model, a univariate model. That associative memory is held in the connective structure of the system. And because it's associative, it means that the system can generalize, which means that it can find better solutions to constraint optimization problems with experience. And I'll call that systemic intelligence, meaning the ability to find more harmonious configurations that resolve more of the internal conflicts in the system. Let's dig in a little bit and see how that works. So any kind of induction requires modeling underlying regularities. A very simple form of induction is just extrapolation or interpolation. But in multidimensional data sets, like a set of bit strings, we can look for regularities that are to do with the co-occurrence of features. So in this data set, you might notice that the first two bits are always the same, and as are the middle two bits, and the last two bits are always different. And if those are the regularities that you notice, you can represent that by using Hebbian learning to make a model of those associations. Hebbian learning just means the more two things are excited or co-occur, the more you strengthen the connection between them. It models what things go together. So here I'm modeling those with connections that are either blue or red for positive or negative correlations. Now, a correlation model records information about multiple patterns in one point in model space. So one way of filling in the interaction coefficients of the interaction matrix of the associative model produces many, corresponds to many points in the training set. But it also corresponds to some other points that might not have been in the training set. Here's some examples of bit strings that have the same regularity as our model, but they weren't in the original training set. And that's how generalization works. So now we can transfer those ideas of associative learning into a dynamical system represented by a set of state variables connected by a set of connections. And we can use that to represent all sorts of things like species in an ecosystem, particles connected by springs, people in a social network. And if we want to use that dynamical system to model our observations, then we can look at the correlations in our system. And every time we see two variables having the same value, we strengthen the positive connection. And when they have a different value, we strengthen the negative connection. And we'll have a model of those observations. And to find out what's the patterns are that are stored in that model, you randomize the state variables and then let them relax, let the connections tell them what to do. And the behavior of the system will be described by an energy function with fixed point attractors if the connections are symmetric, which they will be if they were put there by Hebbian learning. And the local minima in that energy function correspond to patterns which are stored in the network. If we re-randomize the state variables and relax it again, we arrive at different local optima. And over that distribution, we represent the set of training patterns that we had. Now, a second way in which a dynamical system can be an associative model is to think of a dynamical system as a way of representing a problem. If we have a set of variables where some of the variables need to be positively correlated and some of the variables need to be different, and some of those needs or constraints are stronger than others, then the interactions between the variables represent a problem. Hopfield and Tank showed this as a way of representing connections that told you about the distances between cities in a TSP problem. And then when we randomize the state variables and relax them, our energy function gives us locally optimal solutions to our problem. And repeated relaxation gives us a distribution of locally optimal solutions. So one way of thinking about a dynamical system is it's a place where you can store observations about correlations and then recall them. And another way of thinking about a dynamical system is that the connections represent a problem, and running the system gives us locally optimal solutions to that problem. And if we put those two things together, correlation learning and constraint solving, we get adaptation by induction, which can demonstrate improved optimization ability and improved ability to solve the constraints of the problem. So adaptation by induction works like this. We set up the dynamical system, or we have a dynamical system that describes a problem of constraints, people with conflicting interests. We run the dynamical system, we allow the people to do what they want to do, given the conflicting interests that they have, and that gives us locally optimal solutions. Then we take those locally optimal solutions and we use them to update the weights of the problem. Each locally optimal solution is used to update the interactions. That is the positive feedback on correlations. The more two things co-occur, because there are subpatterns that occur in local optima, the more the connections are changed to make those things occur more. That means that information found by relaxing the state variables is fed back to update the interaction variables. That's the positive feedback on correlations. And that feedback will have the effect of altering the energy function. It will decrease the energy of configurations which are visited most often, widening the basin of attraction for those configurations, and making the system more likely to go to those configurations again in future. But in fact, as we continue our learning, because it's an associative model, it can also enlarge the basin of attraction for new configurations that are solutions it hasn't found before through generalization, such that we may take a starting point that initially went to the left and got stuck in a local optimum, but now goes to the right and finds the global optimum. It learns to find better solutions to the original conflicting constraints. So that's the first two steps in our train here. We've connected positive feedback on correlations, provides unsupervised associative learning, which produces global adaptation ability in a network of simple components. But what we need now is this viscoelastic connection thing. The fact that this is natural, that connections give way slightly under stress, make the current state more likely to co-occur again. So correlation learning of this kind happens naturally. It doesn't need any fancy learning mechanisms or algorithms because it's only positive feedback on correlations. That means that the more two things co-occur, the more the connection between them changes in the manner that makes them co-occur more in future. It's a positive feedback which will occur spontaneously in any dynamical system described by a network of viscoelastic connections. That means that the interactions give way a little under stress. In natural systems, it just means that the connections are relaxing. They're going in the direction that minimize energy of the system. And when they give way in that way, they oppose less the current state configuration of the system. They become more consistent with the current pattern of forcing that the state variables are experiencing, which makes that pattern of forcing more likely to occur again. That's the positive feedback on correlations. So if we had a system of particles connected by springs, then the positions of the particles which determine which springs are in tension and which springs aren't. And the springs will weaken. The ones which are in tension will change, and the ones which are not in tension won't weaken or deform under the stress of the state configuration that they're in. And the interactions change in proportion to the stress that they're under, which means that the interactions accommodate the current state or a differential easing of frustrations in the system. So that provides our left-hand loop here. The right-hand loop is simply relaxing the state variables given the interactions that they have. And the left-hand loop is simply relax the interactions given the states that you have. But it's crucial that the system is pulsed in order to get adaptation by natural induction. That's the shocks or perturbations which reset the state variables and allow the system to find a different local optimum. If you don't do that, it just falls to one local optimum, then the springs relax and you just stay there. and it becomes the first place you go is the only place you'll ever go. But if the system is perturbed and relaxed, then it can have a distribution of experiences, and that enables it to do associative learning in the connections of the system, which enables it to generalize and find better solutions over time. So here's an example. This is a simple numerical illustration of such a system. And initially, we're just relaxing the state variables given the interactions that we have for a particular problem. And what we're interested in is those endpoints. Each of those red dots is a locally optimal solution found without any learning to start with. If we zoom in on that and take some more samples, we have a distribution of locally optimal solutions found, in this case, over 1,000 trials. Now, if we allow the connections in the system to differentially deform under natural induction, the distribution that the system visits changes over time and eventually converges on a particular attractor, meaning that the system learns to find good solutions more reliably. Down is good in this example. In some other cases, it's possible to get it to do not just reinforcing the best thing that it found before, but finding something better than anything it found before. And as the system gets larger, that effect gets stronger, that it can find an attractor, which although it isn't the best possible, there are some gray dots lower than the one that it converges on here, it converges on something that's better than any solution found without learning. Now, this only works if the system is perturbed. Without perturbation, it just fixes on an arbitrary solution. It might be higher sometimes, might be lower other times. But with perturbation, it learns associatively over that distribution and finds configurations which have less frustration between the components or more harmony than could be found through any of those perturbations, any of the results found without learning. And that provides our connection between the network of viscoelastic connections and the global adaptation ability. There's no natural selection here. There's no differential reproduction of entities in a population, not the nodes, not the links, not the network as a whole. And that's possible because the change in the connections is directional. It changes in the direction that reduces energy. It never changes in the direction that increases energy. And that produces positive feedback on correlations, never negative feedback on correlations. That's what Dawkins got wrong when he said there can't be any other mechanism, because he couldn't imagine a mechanism of directed change that would produce adaptation. This means that the universality assumption of Darwinism is not correct. Natural selection isn't the only process capable of producing adaptation spontaneously without being designed or selected for that purpose. And natural induction only requires connections that give way a bit under stress, producing differential easing of frustrated relationships, and pulse, that episodic experience or stress. I'm working with Tim to produce a paper about that, the Universal Darwinism being incorrect. So, of course, not all complex dynamical systems are naturally described as networks, but for those that are, and to the extent that the relationships between components are rarely perfectly elastic, they always give way slightly under stress, then, and that the pressure or forcing that a system experiences is rarely constant, it's hard to stop a system exhibiting natural induction to some extent. But learning theory identifies the conditions or the design principles that will enhance it. Now, natural induction is an algorithm that can be realized in many different substrates. It can be implemented in Hebbian learning between neurons, which will learn to optimize an objective function, or mechanical viscoelasticity in springs, which will learn to minimize the energy of the system better with experience. But it also works for the self-interest acting on relationships in a society with the effect of increasing collective welfare. So if we are two people in a social network and the way that I vote in an election is influenced by the people that I'm friends with in a positive correlation sort of way, but it might also be the case that if I persistently vote in a way that's different from you, maybe I just decrease my friendship with you because it's creating friction in the system. And in so doing, the system then changes the dynamics of the system, because by changing the connections, it changes how I behave. And what natural induction tells us is that it doesn't just change it, it changes it in a way which increases collective welfare. Natural induction can also be implemented by natural selection, acting on the interspecific interactions in an ecosystem with the effect of increasing total biomass. But it's still the same associative learning mechanism, whichever substrate it is you implement it in. Even when natural selection is involved, it's a different adaptive process because it applies in systems where natural selection doesn't, at a system level where the system doesn't reproduce, such as an ecosystem. And it's a different adaptive algorithm because it has different adaptive capabilities. You can find solutions with natural induction that can't be found with natural selection. But the interaction of natural selection and natural induction is interesting because biology is full of dynamical systems that are described by networks, from protein networks to gene regulation networks to ecological community networks. And the interaction coefficients in the networks often change by natural selection through random variation and selection at one level or another. And if you let natural selection modify connections in such a network, it will do so in a manner that eases frustrations. Natural selection doesn't act to make things more difficult, which means that it's a source of positive feedback on correlations. Previous work has shown this on gene regulation networks. But today I'd like to show you an example of natural induction in an ecosystem. So in this example, the state variables are the species densities in an interaction community, and the interactions are the competition coefficients between species. So we have an ecological community network, and we're going to allow the interactions between species to change by natural selection, but by individual level natural selection. There's no population of ecosystems. There's no global feedback saying natural selection should evolve selections in a way that produces some global outcome. It's just individuals within each species are experiencing random variation and selection on their interaction coefficients with other species. And if they change in such a way that makes that individual grow faster than its conspecifics, then it does. That's it, individual level natural selection. So if we set up the initial competition coefficients between species to represent the constraints of a resource conflict problem, then the ecosystem under natural induction conditions should get better at resolving those conflicts. What resource conflict problem shall we use as an example? Well, I would have done random max-2-sat problems like we did with the springs, but Dan's more imaginative than me, so he did Sudoku puzzles and asked the question, can an ecosystem learn to solve Sudoku? So the numbers in the cells are represented by species densities, and the rules of Sudoku are represented by the competition coefficients. So the species representing a number 3 in a particular cell has strong competition coefficients with other 3s, which are in the same row, the same column, or the same box. And it also has strong competition coefficients with all the other numbers that could go in that cell, because you're only allowed to have one number in each cell. It's similar to the setup that Hopfield and Tank used for the traveling salesperson problem, but cooler. So if we set the species densities at random, we don't get very good solutions. Lots of species will be in conflict with others, 2 9s in the same column, 2 9s in the same box, etc., shown in red. If we run the Lotka-Volterra dynamics described by the interaction coefficients, describing the rules of Sudoku, then the configuration gets slightly better until it finds a local optimum. A climax community, in ecological terms, is a locally optimal solution to our puzzle. And there are less conflicts here, but still a lot. If we leave it there and we allow the interactions to evolve slowly, it will simply canalize that configuration of species until that's the only attractor that the system has, in fact. But if instead our ecology is subject to regular shocks, which cause the species densities to be randomized, whilst natural selection is slowly changing the interaction coefficients of the system, then we get a different outcome. And even if we start the system from exactly the same configuration of random initial species densities, when we run the Lotka-Volterra dynamics with the new interaction coefficients, the assembly rules of the climax community are now different. and they now assemble a climax community that has a different combination of species at attractor. In fact, the number of conflicts now is much reduced. This means that the ecosystem has a systemic intelligence that knows how to find more harmonious states than it did at the beginning, where less species are in conflict. If you try it on harder Sudoku puzzles that humans find very difficult, it can still find the perfect solutions sometimes, or much better than random solutions other times. Now, ecosystems are not supposed to be able to solve problems. There isn't any selection at the system level because the system doesn't reproduce. But it is a dynamical system described by a network of viscoelastic connections, and when subject to episodic stress or occasional shock, it adopts adaptive organization, not by natural selection, but by natural induction. This suggests that conditions exist where the biosphere could have adaptive organization, much like the Gaia notions of Lovelock, but much more than homeostatic self-regulation. This is an optimizing principle. Note that shocks or perturbations are essential, and these could be provided at many different timescales and different physical scales. Tides in rock pools, storms on a tropical island, seasons over the years, ice ages over longer timescales, life cycles, or being in or out of a host, or indeed the evolution of interactions among components which were involved in a developmental life cycle of an organism. A sustained pressure, in contrast to this pulsed pressure, would canalize the current solution. Whatever the first solution is you find gets canalized, and that's it. And it wipes out the memory of the system, removes systemic intelligence, giving the system no agility. Now, the view of the relationship between natural selection and natural induction here is interesting when we look at one level and then another level of organization above or below. Specifically, natural selection explains how a link changes in the system. An individual that has a variant link that is less frustrated outcompetes through short-term self-interest other individuals in its species. But this doesn't explain why that was the link that was under pressure to change and not some other link. And more specifically, it doesn't explain why the links that were under pressure to change were exactly those required to increase long-term collective welfare. But natural induction at the level above does explain the structure of the natural selection that was operating at the level below. And if natural selection and natural induction are allowed to work together over multiple levels, the natural induction at one level primes the working together that's necessary to instantiate natural selection at a higher level, as in the transitions in individuality, that then implements a network in which natural induction could occur at the next level up, and so on, priming working together for natural selection at the level above that. Providing a mechanism of deep evolution for multiple transitions in evolution that's equivalent to a multi-scale associative learning machine. By the way, in machine learning context, there's no need to use a population-based model. You can do it with a deep learning neural network that builds a model of your problem layer by layer by sampling local optima and then using that model to sample better local optima and so on. And that can be shown to solve problems that single level evolution can't solve. And in fact, it solves problems that no other model building optimization method can solve at this time. Good job, Jamie. So now let's return to the bigger picture. The same principles extend to social organizations. If each individual changes relationships with others to maximize their individual utility, and the system experiences episodic stress or occasional perturbations or shocks, then the organization of those connections increases long-term collective welfare. The society can have adaptive organization without top-down governance that reduces internal conflict or increases harmony, producing greater total utility. It's a bit like the invisible hand of Adam Smith, perhaps, but much more than simply finding the local Nash equilibrium or just asserting that selfishness is doing all the work. Perhaps it's closer to the social ecological systems of Elinor Ostrom and collective self-governance through multiple nested layers of enterprises, but it's a theory that explains how that can work not just an observation that it can, or an observation that those design principles support it. Of course, it has an obvious flavor of connectedness, not of, well, I'm all right, I survive and you don't, but it's more to do with the relationships between us. It's driven by the differential easing of relationships between entities, not the differential survival and reproduction of entities. And systemic intelligence accumulated, excuse me, over past experience is held not in the parts, but in the conditioned relationships between them. It's not about competition, survival, or selfishness. It's about relationships, connectedness, and organization. They're different prime movers. Natural selection's prime mover, that some things win and some things lose. Some things are retained, some things are discarded. Natural induction's prime mover is the differential easing of frustrated relationships. It's a mechanism of transformational change, not variational change in Elliott-Sober's terminology. Because they're different prime movers, that means there's different design principles needed to improve adaptation. Under natural selection, adaptation is supported by random variation because you don't want bias, and free competition because you don't want collusion, and by allowing some to win and others to lose. You don't want any passengers or handouts or compassion. These are the virtues of selfishness, as Ayn Rand would say. And it's supported by sustained profit, performance, or throughput pressure. The clearer the signal, the better the response. But adaptation under natural induction is supported by a different set of things, by valuing relationships, because that's where the systemic intelligence is held, by letting them mature with experience, which means they need to be able to change. You can't have a rigid top-down organization chart that doesn't change, but they can't be too fluid either. They can't be changing on the same timescales as the major dynamics of the state variables. It's the appropriate learning rate in machine learning terms. And adaptation by natural induction can be supported by creating opportunities for varied experience, by episodic stress, because you can't learn a good model from one experience. And that means that sustained pressure for increased profit or performance indicators or cost reduction or throughput, etc., destroys systemic intelligence. It holds the system in one state and fits the relationships to it. It's like an extreme kind of overfitting where you just fix on one training sample and learn that one to death. And in the same way that overfitting to a specific data set reduces generalization, that's the wrong thing to do if you want systemic intelligence. But what about the logic of self-interest, where I said, well, it's unavoidable that it's rational for me to do the thing that's best for me. But notice that in natural induction, I said that if you accept the concept of an individual and the concept of incentive or utility, you can't get away from that. But the way that you can get away from it is by not accepting the concept of individuality. In natural induction, individuality is a fluid thing, if it's a thing at all. In social networks, taking the stress out of relationships changes the actions of individuals from being compatible with their short-term self-interest to actions which are compatible with long-term collective interest. And the evolving relationships in the biological systems, as relationships evolve between units, they become less of an individual or de-Darwinized. And the system as a whole becomes more of an individual or Darwinized at a higher level of organization. It's all relative and contextual. Relationships define who the individual is and what they want. There's no individual except in relation to others. So natural induction doesn't say that all life is lovely and harmonious, but the principles of learning theory tell us what conditions will enhance systemic intelligence and what will do the opposite. But natural induction is compatible with a worldview that sees our relationships with one another and with nature, not just as resources to be exploited and opportunities to benefit ourselves, but as connections that hold collective knowledge accumulated by experience. It's these relationships that makes the whole smarter than the sum of the parts. And perhaps such a perspective encourages a worldview where we want to treat our relationships with each other and with nature with some suitable reverence. But when we form relationships with others, evolutionarily or personally, our future options are changed, with the consequence that sometimes we're caused to do something different, including sometimes doing things that we didn't want to do before we had those relationships. But this is not merely a regrettable obstacle. the organization of those relationships can be adaptively organized such that the new options or incentives that they present cause self-interested individuals to act in better alignment with long-term collective interest. And a word that people sometimes use to describe relationships that cause us to serve something other than ourselves is love. Not the hallmark kind or the neurochemistry kind, the kind that does real work, the kind that changes what we choose to do, the kind that makes us part of something greater than we are as individuals. This I offer as an antidote to Universal Darwinism that offers a scientific framework that recognizes that selfishness and competition are not the sole prime movers and naturalizes an incentive to ask, what do we know of each other rather than what's in it for me? So with that, I'll thank you again for attending today, and Dennis for the invitation, and the people that are involved in my network, and invite you to get connected with me.
Well, thank you very much, Richard. Could I ask you to unshare your screen so we can go back to the full panoply of contributors, and I'll ask for questions from the audience. Any questions for
Thank you
Richard?
so much.
So maybe I can start. I wonder how you would feel about the following suggestion, which I think, which I offer completely sympathetically. That what's wrong with Universal Darwinism is that it kind of misunderstands Darwinism. So Dawkins says, well, you know, Darwinism is the only mechanism I know that can produce evolution. And one of the things we might object to is the idea that it's the only mechanism, but the other thing we might object to is that it's a mechanism at all. And one of the interpretations of natural selection is it's not a mechanism, it's not a cause, it's the effect registered at the level of a population or ensemble of all the stuff that goes on at the individual level. And so some of the things that go on at the individual level might be competition, but the other things that go on at the individual level could be natural induction. And so we have populations of entities, and they change in their abstract trait structure as a result of what the individuals do. And that's left entirely open what they do. So for Darwin, they struggle to live, to survive, but that struggle could be manifest as natural induction, but it could be manifest as rigid competition. What goes on there, what causes natural selection is left completely open. And so what you have offered us is a kind of different conception of what the struggle for life consists in. It's natural induction. And in fact, there's lots of evidence to show that you can't get adaptive evolution over populations unless the component individuals in the population are themselves adaptive entities, natural inducers. Would that help, the dialectic?
Yeah. So notice that I didn't say that Darwinism was wrong or that natural selection didn't occur, of course. But I do think that natural induction helps provide a context that explains more than natural selection on its own does. And it does so both at scales below and at scales above, right? So you can think of a population undergoing natural selection where each of the entities in that population are doing natural induction, right? Where they are learners. And the natural selection is tuning their ability to do induction. That's fine. We can evolve brains by natural selection if you like. And the other way around is that even though each of those entities in the system is doing natural selection at the level above, if the natural selection is acting on interactions with other components in the population, then at the system level, that can be doing natural induction. But we can't use natural selection to explain the pattern of organized connections that we get at the system level, because the system level wasn't a unit of selection. So the natural induction can explain that, even though it's natural selection that was the implementing mechanism below. Does that sound all right? You're muted, Dennis.
Yes, we'll have to discuss this at greater length, but we'll get the opportunity to do this. We have a whole battery of questions. So, we'll start with Jason and then Tyler and then for me. Jason? Jason
Sure, thanks
Platt?
so much.
Sure,
Yeah, thanks for this very provocative and interesting talk, Richard.
Nice to meet you, Jason.
Good to meet you. Yeah, so one of the elements of your model that was most novel to me was this pulse idea. And I was wondering if you could maybe speak a little bit more about exactly how this pulse functions, because I'm not exactly following why a pulse or shock to the system would always lead like inevitably to improvement, to an improved solution. Like, why won't it harm the system half the time or utterly destroy the system?
Right. Good. So good. So it's not the shocks or perturbations that are doing the improvement, right? The thing that's doing the improvement is the differential relaxation of the connections. The shocks or perturbations are just to give the system an opportunity to have more than one experience. So if you randomize the state variables and let them fall to a local attractor, at that local attractor, the learning that happens is by differentially easing the frustrations in the connections. But if you don't randomize the state variables and let them find a different attractor, then you don't have a distribution to learn over. You just have one sample to learn over. It just learns that one pattern. But if it has it's like saying you can't learn a class from a single example, right? You have to have each of the local attractors is a point in your training set, and you have to have a distribution of them if you want to generalize.
Okay, I guess my lingering question is, so, but if the system was already pretty close to the ideal fit, and isn't there the risk that the perturbation will cause this relaxation of the relationships in a way that will actually lead to a worse solution next time?
Oh yeah, sure. Each individual perturbation makes things worse, right? It randomizes the state variables, now it has no bloody idea what it's doing, right? But the interaction coefficients are unchanged by that perturbation. It's the state variables which are perturbed, right?
Okay.
The interaction coefficients change slowly and incrementally whilst the state variables are undergoing that perturbation, right?
Okay.
So when you randomize the state variables, you've now just randomized your solution, right? And that's always going to make things worse. But if the interaction coefficients are changing slowly, they hold a memory of the good places that it's been before, and it makes the system over time more likely to recover from a perturbation more quickly, more likely to go to a place that's good that it's been to before, and through generalization to a place that it's never been to before, but is better than any of them.
Okay, I think that helps fill in the gap that I was missing. Yeah, thank you.
Okay, cool. Good question. Thank you.
Thank you. Tyler Volk.
Okay.
Hi, Tyler.
Hey, Richard. Hi. Great to see you. Fantastic talk. I really put your ideas together in a very coherent and wonderful way. So I think things were fairly understandable with the springs, in terms of what is tension, what is relaxing to be in a different shape. But I'm going to have to, and we've talked about this a bit before, but what does it mean when you get to ecosystem and species? What for example, does easing of frustrations mean?
Yeah. So in the ecological model that I showed you there, what's the analogy of the two particles connected by a spring, right? So the two particles are the two species densities, and the spring between them is the competition coefficient, a symmetric competition coefficient between them. And the way in which the spring changes is through random variation and selection on that competition coefficient at the individual level. And what you need is that the rate of change in the connection is proportional to the product of the species density. That gives you Hebb's rule. And the reason that it gives you that, the reason that you get that, is because if two species are never in high density at the same time, then the competition coefficient between those species don't matter to either of them. But if those two species are in high density at the same time, then the competition coefficient between them does matter. Now, it's always the case that you want to reduce a competition coefficient, not increase it. But which ones are more important to you to reduce than others depends on which species were in high density at the same time.
And so then overall, in what you're calling learning and getting better in, let's say, an ecosystem or a biosphere sense, would be global reduction in total competition summed up over the entire system?
Yeah. Now that's sort of obvious because you're allowing the competition coefficients to change, right?
Yeah.
So even if you didn't do any perturbation or anything clever, and you just say, well, let's let natural selection change the competition coefficients.
Right.
So they change in the direction that reduces competition. So the total competition has gone down.
Okay.
I don't get it. That seems like a non-result, right? But if the way in which the competition coefficients changes the dynamical attractors of the system, and if you look at what those state configurations, how much conflict there was with the original constraints, not that the new ones are relaxed, but even if you look at what that state configuration was with the original constraints, there's less conflict in the system. There's less competition in the system than there was at the other attractors that you went to.
Using natural selection.
Yeah, using natural induction.
So wait. I thought you were comparing natural induction to a system that has natural selection in it.
That's
but
right.
There's a natural induction at a higher level.
Yeah. Yeah. So if there wasn't any natural induction, but there was still natural selection, right, it would relax to a particular climax community, an attractor state. Yes. And then natural selection would change the interaction coefficients, but it wouldn't change the state. It would just stay at whatever configuration it was at. And all of
what do you mean by state? Because you're still going to be perturbing it. There's still climatic changes. So natural selection can still be working on that, on the whole system.
Well, if there are such perturbations and they cause it to visit a distribution of attractors, then natural induction would be organizing which interactions were changing.
Okay.
I mean, I don't need to introduce.
So are you saying though, you cannot have the system you're setting up, you cannot not have natural induction happen?
You could have natural induction happen in a degenerate way, right? It's like a learning system that just finds the answer that's obvious, a crappy answer that's not very good, that's obvious. And then it learns that one answer such that whatever question you ask it in future, it can never answer anything else except that answer, right? So it's still easing the frustrations in the system to increase the dynamical attractor of that state, but it won't be a good one. Right? It's like saying that if I do rote learning with one data sample, I'm still doing learning. Well, sort of, yeah.
So right? Do you think
just one memory?
Yeah, Dennis, I'm just follow up one more, and then I gotta let other people talk. But are you, so for example, could you take the biosphere structure or an ecosystem structure and maybe tease out how much of the global collaboration, however, global love you're going to measure, how much of that is due to the natural induction process, and how much of that may be due to the natural selection process? Because ultimately you can't run the ecosystem or biosphere without natural induction, so you can't, but is there some way to tease out relative magnitudes of those?
That's a great question. So if you could rerun the tape of life and you had complete control over all the variables, you could.
Yeah, okay. But by doing some metric on, I don't know, it's your field, not mine, but just
so I mean, if you could, so let's be clear, right? If there wasn't any natural selection, the natural induction wouldn't occur because none of the connections would change, right?
Right.
And if natural selection is occurring and the connections are changing, well, then there must be natural induction occurring, but it wouldn't be very good natural induction unless you also had the perturbations. So I think the thing that's important here really is, in order to say, does it really matter which one we call it then, right? I think that what's really important, should we just call it natural selection with some perturbations, or should we call it natural induction? And I think what matters is how much work is the inductive bias doing? It's like how much work is generalization doing, right?
Right.
So in a learning system, when you say, well, I showed it this training data, and on this training data, it got this performance score, so what, right? But when you test the system on data it hasn't seen before, that's like you've perturbed it to an initial condition that it's never experienced before. Where does it go, right? It's how well does it generalize? That the questions about how well it generalizes enables you to quantify whether the learning in the proper sense of learning, the generalization sense of learning, was actually doing any work or not. But that's a really good question though, Tyler. I'll have to think about that more.
Okay, cool, Richard. Thank you. Great talk.
So we have a question in the chat from Michael Inslick that's about this relationship between natural induction and natural selection. Michael says, is it possible that natural induction is the process via which natural selection works? And he says this has, it reminds him of the so-called group selection controversies that we had in the 80s and beyond. Could you just say a little bit about what this connection between selection and induction is?
Why do I have a message that says, please ask the host to give you permission to record? I wasn't trying to record. I'm going to close that message. Is it possible that natural induction is the process via which natural selection works? Well, in case you were thinking that my talk wasn't controversial enough, sometimes I'm inclined to say that not only is natural induction a different adaptive process from natural selection, and not only is natural induction a better adaptive process than natural selection, but that natural selection isn't an adaptive process at all.
Yeah.
Natural selection is just a ball rolling downhill to a local optimum. It's literally the same as a ball rolling downhill to a local optimum, except usually we imagine it going up instead of down. So if that's adaptation, well, then a ball running downhill is really adaptation. You have to look at a ball that's found a local minimum and say, wow, look how good it is at finding the local minimum. I don't buy that that's really adaptation at all. Or if it is, let's call it adaptation type 0. If you're able to, if you see a ball which doesn't roll down the local gradient, but sometimes goes uphill in a way which is directed towards optima which are further down, then you'd say, okay, now I'm surprised. Now that's doing something that looks intelligent. It's doing something that has knowledge or doing something that's goal-directed. But that's exactly what happens in a system under natural induction, that it goes through state configurations that it wouldn't have gone through because the new interactions change the incentives of the particles. And you can see that the energy as measured on the original interactions goes up in order to go down. I don't know if I was really answering the question that was asked there, but I think that natural induction has something to say, not only about the kinds of systems where natural selection doesn't apply, but it has something to say about the processes of adaptation that are involved in all biological evolution. That it's another way of saying it is that I don't really think there's any evolution without the evolution of evolvability. And the mechanism of evolvability is really about how do you have an ability to be adapted or to be easily adapt to an environment that's genuinely novel, right? If you've done it already, then that's not evolvability, that's just evolution. If you haven't done it already, how could it be possible? And it can be possible because you can generalize from past selective environments to novel selective environments. And that ability to do that, you can use the framework of learning theory to explain how the evolution of evolvability works. Because if you don't make assumptions about, you can say, well, natural selection only needs variation, selection, and inheritance. But if you don't have suitable variation and suitable selection and suitable inheritance, it doesn't work. Why is it suitable, right? Out of the kinds of variation that you could have, you get variation that includes something that at least sometimes is an improvement. I'm waffling now. I'm pretty sure I'm not answering the question. Certainly does. Yeah.
For me.
Thanks very much, Richard. So some people think that developmental capacities of organisms are a source of adaptation when natural selection is not involved, like phenotypic plasticity or niche construction. So my question is, what's the relation between this developmental form of adaptation and natural induction? Can we establish a formal equivalence between developmental adaptation and natural induction, or are they really two different sources of adaptation?
So So the majority of work that I've done on this topic has actually been done on gene regulation networks rather than ecological networks. And there I show that a gene regulation network that's evolved to produce a particular phenotype will change connections in the regulatory interactions in a way that produces a memory of the phenotypes that have been selected in the past. But in addition, that means that you have a single gene network that produces multiple phenotypes that have been selected over its history. But because it can generalize, it can also produce novel phenotypes that are from the same class, even if it hasn't been selected for in the past. And that ability to generalize can enable it to produce novel phenotypes that haven't been selected for in the past, which can improve its evolvability and hence increase its ability to evolve more rapidly in a rugged fitness landscape. And that work, I think, is an example of how the evolution of developmental organization is an actor in, it produces developmental organization, which is an actor in the evolutionary process, that the developmental organization knows something about the fitness landscape from past experience. And it's not just how good is the point where I am now, right? It knows something about the structure of the fitness landscape from its past experience. So there's nothing, the trouble with the phenotype first arguments, right, is, okay, it's kind of obvious that if you had an adaptive phenotypic plasticity process, then that could adapt more quickly than genetic evolution could. And in fact, you could get adaptation at the phenotypic level without any change at the genetic level. And then maybe genetic evolution would follow behind through accommodation or assimilation. But the problem with that sort of argument is, yeah, but how did you get the adaptive phenotypic variation in the first place, right? It could have only have been put there through natural selection because that kind of plasticity was good in the past, demonstrated to be good in the past, produced fit phenotypes in the past. But when you recognize that natural selection acting on the interaction coefficients of a generative network can generalize, that changes that a bit. It means that the adaptive plasticity that you have is that induction is an important part of what's happening, that it's not just reinforcing things that you've already seen to be good. So I do think that it has something to say about that, yeah.
Super, thanks very much. This is a little difficult to resist. We have a question from Hawaii. So Lee Altenberg is there from Honolulu. Lee, do you want to ask
hi, Lee.
Hi, Richard. Fantastic.
Oh, hi, nice to see you.
Great to see you. So three questions came to mind from your presentation. One is the work by Kaufman and Johnson on the coevolution to the edge of chaos, their NKC model. I'm just wondering, that would seem to fit somehow into your framework, but I'm wondering how specifically. The second question was about your concept of love. It's reminiscent of Martin Luther King Jr.'s concept of agape love. And I'm wondering if you had any reflection on that. And then third is I
don't know what that is, but I'll take it. Yeah.
Okay. Crucial to Jeremy England's ideas is this notion of repeated perturbation, and I'm wondering how that dovetails into your picture.
Right. So thank you. So the first one about self-organization. So something that I can say about that is just that order for free isn't adaptation for free. So the fact that a system organizes itself is one thing, and that the past experience of a dynamical system through the way in which it's been forced or conditioned by that past experience might change the organization of the system, that's fine. But it's not the same as showing that a system can produce adaptation. So that's controversial territory in biological terms, because people say, oh, what do you mean by adaptation anyway? Surely the only reasonable concept of adaptation is Darwinian fitness. But if you're talking about a mechanism of adaptation that isn't natural selection, then Darwinian fitness isn't the right metric for that. So I use the ability to get better at finding solutions to complex combinatorial optimization problems as a proxy for adaptation, right? That these are special configurations, not because they're ordered, but because they're good solutions to a problem. That they satisfy more of the conflicting constraints between variables or something. And it hasn't been shown with self-organization in the self-organization framework that can do that. But I think that we're all reaching for the same sort of thing, right? We're all reaching for how is it that a system can have its organization changed over its experience, changed over time in such a way that it improves. And I think that what I'm showing here shows that more concretely.
Well, actually, so I had a different notion from Kaufman that I was referring to, which is, so they just have, it's a pure adaptive model, but where you have one species adaptive landscape is determined by the phenotype of the other species.
Oh yeah.
And they can adjust the connectivity in terms of how much does the adaptive landscape of one species get warped by the adaptation of the first species.
Yeah.
And so the
species don't, but the designer does, right? By choosing.
Yes, right.
C. Yeah.
So they find that under lower levels of connectivity, they co-evolve to a very stable and also highly fit landscape. When their connectivity is extreme, then it just goes into a chaotic coevolution. And then they find there's this intermediate realm where they go to higher levels of mutual adaptation, and that's what they call the edge of chaos. So and then so the hand waving is that the nature should somehow tune their level of interaction to this intermediate level. And so that I mean that's so that's pure, well, it's not, I mean, it's pure adaptation, but generating an interesting kind of level of frustration. And so
yeah, so I can't tell there whether those observations are about the parameters of the problem, right? So if you have a problem where there aren't that many interactions, it's easy. If you have a problem where there are too many interactions, it's impossible. And just in between, you have a problem which is solvable but hard, right? And C is a bit like that parameter, but it's a bit like K in the NK landscape. But whether we're talking about an adaptive process of changing the interaction coefficients in a way that changes the system's ability to find solutions or not, it's not so clear to me that was there. Do I read you right?
Yes. Yeah.
Super.
The Martin Luther King thing, I'll have to look up. I'm sorry, excuse my ignorance on that. What was the third one?
Jeremy England's ideas, trying to get thermodynamics to explain basically organization of adaptation, and intrinsic to that, necessary to that, is this idea of regular perturbation of the environment. And it seems, at least on the pattern level, that it's the same thing as your viscoelasticity.
Okay, good. Well, I'll have to look that up then. The there's similar stuff in other parts, in other literature as well, the Ross Ashby's ultra stability stuff, where you have, that when it goes outside of its essential range, then the connections get rewired. But the rewiring there is random, whereas the rewiring here is directed. And because it's in Ross Ashby's, because it's random, you can only get satisficing, it can't get optimizing. So I don't know where that other work, whether that other work might connect with that as well, but I'll have to look that up. Thank you.
Right.
You're always giving me stuff I need to read, but that's
and likewise.
That's a gift. Thank you.
Thanks, Lee. Nice to see you. We have 4 minutes and 2 hands and a question in the chat. Let's see if we can get through them all. Jillian?
Okay, I think I see 3 hands actually, Dennis. So,
oh yes, a new one.
Yes, friends. And Richard, fantastic. I think you win the prize for the session that has most made us miss the fact that we can go for drinks and dinner afterwards to continue the conversation. So I have about 12 questions here. I'm just going to ask you maybe for the purposes for this audience. So the implications for the effort to build artificial general intelligence. So that's one of the reasons that I've been interested in these connections, because I think there's a heavy influence of that Darwinian model on the way for some organizations, for example, are building multi-agent systems, with the idea that well, if you create enough competition and give them enough data, they'll evolve more general forms of intelligence.
Sure.
And so which I'm really skeptical about. I think about, I mean, I'm sort of in the Ostrom world of institutional thinking and normative systems. But I'm just wondering about the implications for thinking about natural induction for how we approach the challenge of building artificial general intelligence, if there is an
Well, yeah, so one implication is that I think that the idea that, well, natural selection produced amazing intelligence in biology, therefore all we need to do artificial intelligence is artificial selection, is, you know, an artificial implementation of natural selection is very naive. That I don't think that's going to work. The other thing that I can offer is that inducing a deep model, so deep learning has been used in classification regression problems with great success, of course. It hasn't been used previously in optimization problems, and the deep optimization method that my student developed, Jimmy Caldwell, uses a deep learning model to induce the structure of a problem, and then with that structure finds better solutions to the problem, and then from that distribution induces another layer in the network and so on. So it was originally inspired by evolutionary transitions and individuality, that you rescale the evolutionary process with each layer of structure that you build. But you know, you don't need to think of it in evolutionary terms. You can just think of it as a deep induction model. I think that's got some potential for learning to solve problems better with experience that we haven't seen before on toy problems, because I only do toy problems. Deep optimization shows that it can solve some problems in polynomial time that all the other model-based optimization methods that we tried take exponential time. They're not just, you know, 5% better, but a polynomial versus exponential distinction, because it's doing this hierarchical abstraction that the other methods can't do. So, you know, yeah, maybe. But definitely just saying, oh, natural selection can do it, that's not enough.
Yeah, thanks. More to discuss. Thanks so much, Richard.
Thanks for your question, Gillian.
So on that decisive note, maybe we should end. So we still have 4 questions to go. So after we sign off, Richard, would you be available to hang on for another 10, 15 minutes? And we'll.
Oh, I'm very happy to. I'm really pleased to get such fantastic questions on this, but I'm very happy for everybody that's been here. It's great to make a connection with you. And if you need to go, of course, I shan't be offended, but I'm very happy to stay and talk to anyone that wants to. We
have questions from Joshua, Avery, Franz, and somebody else, I believe. So if you still want to ask your questions, hang on a bit. We'll just say goodbye to Richard and let everyone go, and then we'll continue the discussion later on. So Richard, thank you. What a great way to start our new term of SRI seminars.
Oh, thank you so much for the invitation. I've really enjoyed it.
Oh, and Tom is there too. Yes, of course. And I have to admit that I had really high expectations for this, but you've completely exceeded them. So thanks very much. It's lovely to see you again. Bye-bye, everyone.
Thank you so much.
So Tom, Joshua, Avery, and Franz, if you can hang on, we'll continue the discussion with Richard. Tom, I think you've been waiting the longest of everyone.
Thank you. Thank you for sticking around. I just wanted to know if you've done any work on establishing a threshold when a system, when the connections between parties in a system might satisfy whatever requirement is to be to engage in the natural induction. I mean, it all seems a little abstract right now, and I just wonder if you've thought of ways to tell, well, these interactions are too loose to do anything useful, or these interactions are a little tighter, and so now we can expect to get something out of it. Is there work along those lines?
I guess the only thing that I could offer there is that these are issues that come up a lot in machine learning. right? When you're trying to get a neural network to learn something, having a learning rate that modifies connections too easily will overfit. Having learning rate that modifies connections too slowly will take too long to learn. And tuning it right and early stopping, affects your ability to generalize and the rest of it. So in systems where connections are too rigid, you wouldn't get any learning. In systems where connections are changing, they need to change at a different time scale from the dynamic variables. They need to be slower. The structural variables need to be slower than the state variables. Those sorts of things I can say, but that's the only sort of, I guess that might be still in the still too abstract category, perhaps for your question.
Yeah, I was more asking, here's some rabbits in a field and some flowers and foxes and what have you. Is there a way to say, okay, this system is now coupled, or the nodes in the system are now coupled in a way that we can expect to see induction, or these nodes are not coupled well enough to see induction?
Right, so the amount of coupling at a particular moment in time wouldn't tell us whether the system was a product of natural induction or doing natural induction. It would be the plasticity of those connections, the ability of those connections to change over time that would tell us its capacity for doing induction. Yeah.
Right, but there isn't, you don't really have a way to identify a threshold of yes, it's happening now, or no, this is inadequate.
So I guess that's a bit related to Tyler's question of how could you say, can you say how much of the change in the system is attributable to selection versus induction? I think I would have to come back to whether, how much you need a concept of generalization, how much you need the concept of induction, really, how much you need the concept of generalization in order to explain what's happening.
Okay.
So if it wasn't being perturbed and the connections were just changing directionally, you wouldn't need natural induction to explain what was happening.
Okay.
For example.
Thank you.
Thanks,
Thank
Tom.
you very
I
much.
also just add that I thought it was funny, your remark. I also span the computer science and biology world. And in computer science, you're always talking about balls rolling down hills. And in biology, you're always talking about climbing optimization peaks.
Yeah.
Same math, but for some reason,
one of them is supposed to be dull and the other one is supposed to be exciting, but they're exactly the same maths. I don't get it.
Yes. Anyway, thank you very much.
Thanks so much, Tom. I hope everybody appreciated my induction joke as well earlier, but I couldn't see anybody's faces.
I liked it.
I did.
Joshua.
Hi, Richard.
Hi, Josh.
Hi, everyone. It's a wonderful talk, Richard. Of course, I'm not at all surprised by that. Just for the audience, I work with Richard a bit at the moment. And
Joshua is one of my co-authors on the deep optimization work with Jamie Caldwell that I was mentioning.
Yeah, and we've known each other since about 1998, I think. So I was doing my PhD at roughly the same time as Richard, and
yeah,
I had a very good intuition.
Yeah,
I had a very good intuition that he would go quite far. And anyway, so my question is actually about intuition a bit as well. So this is a kind of habit I have as well with Richard, that I often tell him things that he's done, have been done many times before, and he's very good at putting up with that and telling me that, yeah, but this is I'm finding a new way to do this, and of course that's right. But here's another one of those. So when I was doing my master's project, I had the intuition that just perturbing an evolutionary algorithm would make it generalize better, and that was like well before I had very much experience about machine learning or anything. And so in my master's thesis, that is the algorithm that I proposed for training neural networks with the evolutionary system, where it's kind of like you just perturb it really a lot, and it does generalize better. And I had no theory behind that. It was just a pure intuition, and it's not a famous paper or anything. But then later on, when I was doing my PhD, I came across this idea of multiploidy, and the fact that we have genetic systems that have diploid or multiploid genes. So and they kind of remember something about where they were in the past. And then when they get perturbed, they kind of remember that past thing, and that again gives better performance. It's not just more robust performance, but they seem to generalize better and learn better. So I wondered whether there was any connection with those multiploid genetic algorithms and things that you are mentioning today.
Yeah, polyploidy. And, it's related to Dawkins' notion of Book of the Dead as well, right? That you have, genes that are switched off, but that are holding a memory of past selection.
Yep.
So a couple of things. So the perturbation, right? We'd want to check whether the perturbation was doing something more than simulated annealing does by allowing occasional upward travel so that you can then do further downward travel. Mm-hmm. And we'd want to know that the perturbation was enabling it to visit different attractors over which it was doing generalization rather than just arbitrarily escaping local optima. And the polyploidy case, likewise, whilst that's a type of memory, I would be interested to know whether there's any reason to believe that it was an associative memory. Because if it isn't about learning the correlations between things, right? If it's just like a handprint in clay, right? That's just a univariate model.
Yeah.
Then it can't do any generalization, right? So clay can take an imprint and hold a memory, but it can't do any generalization because it isn't associative. It's a one-for-one memory of the stress that the system has experienced. So if a set of chromosomes is copied, held in reserve, and another set is adapted, I want to know whether that's learning anything about the interactions between the variables or whether it's just storing a canned result. That's what I'd want to know about that.
Mm-hmm. That's a good question. And I'm not familiar enough with, like, there were kind of different complexities of multiploid models. Perhaps some of them had that associative mechanism or not. But anyway, I'm in England and it's quite late at night, as you know, Richard, and I'm getting a bit drunk as I'm sitting here with Agnieszka, who you also know. So I'll leave it at that. Thanks very much.
Nice to see you, Josh.
We'll leave you to your evening, Josh. We've got 3 questions, and I think we'll close it off at that because, as Josh just said, it's late where Richard is, and he has earned his rest. So, Franz.
Hi, Richard. Great talk. I'm glad that I know you're familiar with. You guys talk a lot, so I've seen you before. It was a cool talk then too. My question specifically about the time scales that typically there's like arguments for evolution that there's a certain amount of time that needs to have been passed for this to happen. That was famously Lord Kelvin was opposed to the idea of natural selection initially because he was not agreeing with the estimates of the sun that later on got turned wrong. But so I'm wondering now that you make a lot of arguments about the natural selection kind of goes down more the hill. It's more of like you just follow the local optimum, whereas natural induction allows you to actually kind of go off from that, and it's more dynamic. It allows interaction. And in my own work, I'm also really interested in these aspects of co-evolution, of basically co-adaptation, where you just have a lot of time scales, different dynamics working together. That to me look like that would be really hard to solve in a purely natural selection scenario. And there's a lot of literature on the machine learning that actually probes that, and they have to make amendments and extensions to genetic algorithms, for example, where they have to include certain adaptive properties that in the end turn into learning paradigms. So I'm wondering if you are aware of any kind of like really hard estimates on what like natural selection would have to do to cope with the timescales that we know exist, not just from the timescales in the physical environment, but also the more species you get interacting in those environments, the more complexity you get, and the more you have to kind of allow time for this to be able to solve it.
Yeah, So I'm not very good with absolutes, right? So computer scientists like to answer questions in terms of, well, is the difference more or less than a factor of 2, rather than, what's the scaling like, rather than what are the absolute numbers like. The only person I've seen who was attempting to do estimates of whether there was enough time for biology to have done the natural selection we claim it to have done was Dan Fisher, a physicist at Harvard. I guess that all that I can add to that is that I can show that there will be some problems in which natural induction can find solutions faster than natural selection can. And indeed, if you're talking about natural selection that doesn't have any perturbations, then natural selection would be stuck forever, whereas natural induction can learn from those local optima to do better. So the time complexities in computational terms are different, which would mean that for the same amount of churn, you could get more bang for your buck. I mean, I don't know if that really, how to quantify that in absolute terms about whether or not it explains, you know, the quantity of natural selection that's possible. I'm not clear on though.
Okay, thanks.
Super, thank you very much. Avery.
Hi, yeah, thanks. So I wanted to ask about the Anthropocene, and I was trying to think about, can you hear me all right?
About the what, sorry?
The Anthropocene. I was wondering how natural induction speaks to some of that conversation. So would you think of the Anthropocene as something like a perturbation? Would you say this is a new state of adaptation? And I think mainly what I was trying to make sure I understood is whether ultimately natural induction is a normative model about ecological communities, or if it's a descriptive model about sort of any metastable system.
Yeah, is it just, am I just telling you how it is, or am I telling you what you should do?
Yeah, maybe, yes, something like that. But where does the Anthropocene fit in to this?
I'm not sure how much I can speak to that. So certainly you know, in systems of that scale, there'll be many different nested hierarchical levels of organization with perturbations and learning possible in networks of different scales and different time scales all going on at the same time. With respect to, you know, am I just describing things, or am I saying, is it you know, are they design principles that could improve things, if I'm understanding your question correctly? I think that if you think that what we do can influence what happens next, if you just take us to be, well, we just are what we are and we just do what we do, then there's no conversation to be had. But if you think that what we can do can influence what happens next, then there are questions about which actions would produce which outcomes. And I can say something about that, right? That if you apply a sustained performance indicator pressure, it'll just make it worse, right? You should allow the system to have more organic experience so that it can learn over a distribution in order to get some bottom-up systemic intelligence in the system. I don't know if that's helpful, but it's about the level that my thinking's at so far.
Yeah, no, thanks. That's really interesting. Thank you.
Thanks, Avery.
Thanks, Avery. Okay, so we have Adam Davis and Jason winning, and let's make them quick so that Richard could get some rest. Adam, go ahead.
Hi, Adam. How nice to see you.
Yeah, it's been a while. Yeah. So I actually did my PhD. Richard was one of my supervisors, and we haven't seen each other for a long time. But I got this email, and yeah, really, I caught the sort of last half of the talk, and I think it's really great to see how far things have come, and just your articulation of the ideas and how solid it's become. So yeah, it's great. So and brilliant
talk.
Thanks, Adam. And I haven't thought about this stuff for a while, but I'll super quickly, just to follow on a point that Avery made, as you were talking about perturbations and that kind of thing, I was thinking, you know, there have been periodic mass extinctions throughout the geological record, right? And you also, I mean, you could fit that model somewhat to, there is a fundamental kind of long-term, whether it's a sort of like genotype, phenotype map kind of things, there's a long-term memory there that's learning. And then you kind of reset everything when a mass extinction happens, and then the system gets to relax back to some new optimum. And perhaps, I guess what I'm saying is, have you got any models like that, or have you thought about that could be an essential part of how we end up with greater ecosystem complexity, and in which case, yeah, maybe the current mass extinction that we're inflicting on the world is a long-term, necessary part of a much bigger process?
There's always an optimistic way to look at things, isn't there? Right? Glass half full sort of thing.
Yep.
Yeah. So the mass extinctions, periodic mass extinctions, I do wonder, things like, the conditions for life to evolve on a planet might involve things like, well, if it doesn't have a moon that produces tides so that the rock pools are perturbed and they have a different chance twice a day to have a go at that, then it wouldn't work, right? If those were the places where life sprung forth, that you'd need that some kind of perturbation in the systems to make that work. But there are all sorts of different timescales of perturbations, and the mass extinctions ones are a completely different timescale of perturbation. But if you were looking for something planet-sized to be adapted, you'd need something of that sort of timescale to do the perturbations, right?
Yeah.
In order for the planet to learn, the planet has to have multiple experiences, and a single thought for the planet takes a long time.
Yeah.
I don't know if it needs to be max extinction sort of time, and there can be fractal, right? There can be lots of different levels of perturbation and lots of different levels of learning happening at the same time too. But yeah, it's all good to me. It's all in the mix of different time scales and scales of variation and scales of perturbation that could contribute to it. Yeah.
Interesting. Yeah, super interesting. Thanks. I'll leave it at that because I know we got time. But yeah.
Thanks, Adam.
Thanks, Adam. So, final word, Jason.
You're muted.
Sorry, I'll cut straight to the chase. So, why do you think that natural selection is competition based, but something like an associative learning network is not competition based? Why not think of, if you have an algorithm that's resulting in differential outcomes of connection strengths, and you have the potential for a network developing, some connections become really weak, or you have some nodes that have really low connectivity, or you have a lot of inequality across the network of connection strengths. Why not say that you have competition for connection strengths and connectivity of nodes and things like that?
Sure, good. So that's just a question of whether you're looking up in scale or looking down in scale, right? So I've got a connection that's changing. Why is it changing? If I look down in scale, then it's saying, well, because there were multiple different variants of this connection, and some of the connections survived and some of the connections didn't, right? It's a competitive explanation of why the connections changed. So an individual that has this competition coefficient does better than an individual that has that competition coefficient, and that's why the connection changed. But when you look upwards in scale, you're asking different questions. You're saying, but wait a minute, why was this the connection that was under a pressure to change, and not some other connection that was under a pressure to change? And that's because, well, that was described by the configuration that the system was in. That's why it had that pressure. And when you take a sort of natural selection explanation, they just say, well, that's somebody else's problem. Why the selection coefficients were the way they were, that's somebody else's problem. Well, I'll just tell you how the gene frequencies change as a result of those selection coefficients. But if the selection coefficients were like this, then the connections would change in a way that made the system smarter. But if the selection coefficients were like that, then the connections would change in a way that made it dumber. Why do they change in a way that make it smarter? Well, natural induction, explains why the organization changes in that direction and not the other direction. And that's so looking upwards to see, well, why were the selection coefficients on this connection the way they were? That needs that systemic view to understand that organization.
But the competition is still so I guess it's kind of like, you know, if somebody like Hayek, who, you know, wanted to model free market capitalism using things like neural nets or, you know, Hebbian learning and things like that, wouldn't he say something similar that, well, if you look at it your way, free market capitalism isn't really a competition-based model, because it's, you know, it's doing this larger scale optimization and doing problem solving. But doesn't that point of view miss the point that it's the competition between individuals is really important, and you don't want to miss that. And that's, if you're thinking about, is this system competition based or is it cooperation based, you really have to look at that individual level for that.
So the reason that I went to the trouble of doing a model that's just built of springs was so that I could show that natural induction is an adaptive mechanism that doesn't need any natural selection. But in the example of the ecosystem, well, yeah, I mean, it totally is natural selection that's changing the connections. And if you take away the natural selection, then none of the connections change. And if none of the connections change, then you're not doing any natural induction. So both are true, right? If you look downwards about how did the connection change, its natural selection and competition was necessary to do that. If you're looking at why was this a connection that changed, it's natural induction that explains why that organizational pattern was the organizational pattern that the system was learning. So I think it's okay to look at those both ways. But when you say, because the system is driven by competition and you need competition to make things work, if you take that to mean that we should regulate in such a way that prevents collusion, we should regulate in such a way that relationships are disallowed so that the market stays free, then you're missing the point, because the systemic intelligence is in the connections between things, not in the competition. It's the organization of the relationships, not the competition, that makes things smart.
Okay. Thank you.
No, thanks so much, Jason. Thank you so much, Dennis. Thanks for hanging on. I've really, really enjoyed today. What a fantastic set of questions. Really enjoyed myself. Thank you so much.
Well, thank you so much. And I'll talk to you soon. But anyway, thanks so much. Have a good rest of your evening. And anyway, thanks, everyone. Hey, thanks
everyone.
Coming from Hawaii, Lee. That's great. Thanks, Jack.
Bye. Lovely to see everyone. Thank you.
Bye-bye.
Bye, everyone.